Good morning, cadets. Yesterday we learned about a solenoid and we found out the magnetic field due to current carrying solenoid, right? Let us solve one simple problem based on solenoid. A solenoid of length 0.5 meter has a radius of 1 centimeter. Let us say this is a solenoid of length half meter having some 500 turns with a radius of 1 centimeter. And it is made up of 500 turns. Let us say it is having 500 turns. It carries a current of 5 ampere. It is carrying a current of 5 ampere. What is the magnitude of magnetic field inside the solenoid? So, it is directly given that it is a solenoid. If it is not given that it is a solenoid, then you have to verify the length of this solenoid is very much greater than the radius. So, that is to be verified first. If it is greater than radius, if the length is very much greater than radius, then only we can apply the equation of magnetic field of a long solenoid, right? Here L is equal to 0.5 meter and radius R is equal to 1 centimeter, that is 0.01 meter. So, just take the radius ratio, take the ratio L by R. If you take L by R, you will get 0.5 divided by 0.01 meter. So, this implies 5 divided by 0.1, that is 50. This gives you 50. It means L is 50 times the radius. So, this implies L is very much greater than radius. Now, we can apply the equation of the magnetic field due to a solenoid. We have B equal to mu naught N I. Here, unless otherwise mentioned, what is the core inside, what is the space that is filled inside, we need to consider that it is a free space. Free space means either vacuum or air. So, we need to take mu naught, permeability of free space, and then N, where N is the number of turns per unit length and I is the current. So, first we have to calculate the number of turns per unit length. N, number of turns per unit length, is given by N by L, where you know capital N, number of turns of the entire solenoid is 500 and the length of the solenoid is given 0.5 meter. So, that gives us number of turns per unit length. So, 500 divided by 0.5. So, this gives us number of turns per unit length. That is, if you calculate, it comes out to be 1000 turns. 1000 turns per meter. 1000 turns per meter. That's how we have to write. It is per unit length. In SI unit, it is so many turns per unit length, that is per meter. So, now we can substitute what is the value of mu naught and I N. So, we get the magnetic field. Therefore, magnetic field B is equal to 4 pi into 10 raised to minus 7. That is the value of permeability of free space into N 1000 into the current. Current is 5 ampere. So, you can just calculate 5 4s are 20, 20 into pi into 10 raised to minus 7 and 10 raised to 3. It becomes 10 raised to minus 4. Minus 7 plus 3, it becomes 10 raised to minus 4. So, 20 into pi you have to do. So, this can be written as 2 pi. 2 pi into 10 raised to minus 3 Tesla. 2 pi means 2 into 3.14. Thus, magnetic field B becomes 6.28 into 10 raised to minus 3 Tesla. That is 6.28 millitesla. 6.28 millitesla. This is the magnitude of magnetic field. So, if we take the current in this direction, so using the right hand rule, we can say that magnetic field is towards right. and it produces constant value of magnetic field, that is uniform magnetic field acting towards right side using the right hand rule, right. So one side it acts as a north pole where the magnetic field lines are emerging out, the other side where the magnetic field lines are entering, that acts as a south pole. So the magnitude of magnetic field is 6.28 into 10 raised to minus 3 Tesla. I have written it as 6.28 millitesla. Okay. Now next we are going to learn very important device called as toroid. Yes, now let us learn about what is a toroid. A hollow circular ring, a hollow circular ring on which a large number of turns of wire are closely wound is called as toroid. So I have taken a hollow circular ring, right, on which I have taken a long wire and wound that wire such that the turns are closely wound, and this forms a toroid. It appears as if a long solenoid is bent into the form of a circular ring. If a long solenoid is bent in the form of a circular ring, it forms what is known as the toroid. Then it is interesting, the magnetic field lines will be confined within this ring itself, within this hollow ring. In the interior of this toroid, magnetic field is going to be 0, and exterior of this toroid also magnetic field is going to be 0. So the magnetic field lines are going to be confined only within this circular ring, and they will be forming circular magnetic field lines like this. Circular concentric magnetic field lines. Now you see, when the current I enters from this wire, you can see how the current enters here. At the bottom the current is entering inside, and at the top of the toroid the current is emerging out, right. So this is how one can schematically show the toroid with the help of simple diagram to show the direction of flow of current. So it is entering from this wire, and after completing the toroidal ring it emerges out. As a result, you see the magnetic field lines are confined within the circular ring, within that circular hollow ring. How to find out the direction of these magnetic field lines? Again we make use of the right hand thumb rule. See the current direction, you can see from the top the current is emerging out from the plane of the board, and at the bottom the current is entering inside, and you can see the thumb shows the direction of magnetic field lines. So the magnetic field lines here you can see they are anti-clockwise, the magnetic field lines are anti-clockwise. So wherever the confinement of magnetic field lines is required, which is of this circular shape, there the toroid is being used. As we discussed in the previous video, that solenoid and toroids are used to produce usually constant value of magnetic field, and toroid and solenoid both are being used in a device called as synchrotron, which is a particle accelerator, which is used to accelerate the negatively charged ions and negatively charged particles, right. It is called as synchrotron. So there the toroid is being used. Wherever you require the confinement of magnetic field within this space where you need a circular magnetic field and circular magnetic flux, magnetic field lines, there toroid is being used. Now how to find out magnetic field and how to prove that magnetic field in the interior is 0 and magnetic field in the exterior it is 0. It is confined only in the inside region of the toroid. Let us see how to draw the diagram for that. So, here schematically I am showing 3 regions. This is the interior radius of the ring, and in the interior radius of the ring you can see the current is entering inside. So, current is entering inside means I have to show with cross marks. Current is entering, so I have to show cross marks. Now, this is exterior radius, outer radius of the ring, where you can see the current is emerging. So, schematically I can show dots, same number of dots. So, dots to represent the current emerging out of the plane, cross to represent the current entering into the plane. So, this is how 1, 2, 3, 4, 5, 6, 7, 8 I have taken, 2, 4, 6, 8 I have taken on the exterior or outer radius. Okay. Now, to find the magnetic field, since there is a symmetry, again we apply Ampere Circuit Law. So, to apply Ampere Circuit Law, we are choosing 3 regions. One region in the interior, let us say this is a point P here, right? From the center, let us say this point P is at a distance R1, and another point we are choosing exterior at a point Q, which is at a distance, let me take here point Q, this point is Q, which is at a perpendicular distance, say R2. And one more I am choosing the interior point, that is internal point, which is at a distance, say R. So, you can say R is the mean radius of this ring, So, for these points I am drawing the Amperian loops, and then we are going to apply Ampere Circuit Law. So, to understand this, yes, this is the way current is entering and this is the way current is emerging out. Okay. Now, for this point Q, in order to enclose this point Q, I am drawing Amperian circular loop of radius R2. And to cover this point at an average distance R, this is P, Q, let us say this point is capital R. So, I am drawing one more Amperian loop of radius small r. Now, I can apply Ampere Circuit Law one by one. So, here consider N be the number of turns, N be the number of turns wound on a hollow ring, of radius, let us say average radius small r, right? Okay. Next, first I am choosing point P in the interior of the hollow ring. Let P be a point at distance R1 from the center, at distance r1 from the center O, such that r1 is quite less than r. You can write in interior of ring, interior of hollow ring. Now, since it is of radius r1, now I am applying Ampere circuit law. Applying Ampere's circuit law, we get integral of B dot dl is equal to mu naught times IE, where IE is the current enclosed. When you look at this Amperian circular loop of radius small r1, construct Amperian circular, okay, I did not write that. Applying Ampere circuit law, B dot dl to the constructed Amperian loop, of radius r1, this one. If you look at this interior loop, it does not enclose any current at all. Here, if you draw interior loop, it is of radius, let us say r1, it does not enclose any current. So, naturally B dot dl becomes 0. So, B dot dl, if you calculate, it becomes B into 2 pi r1, B into 2 pi r1, where 2 pi r1 is the total length of this Amperian loop, circumference of this Amperian loop. 2 pi r1 is equal to mu naught times the current enclosed. The current enclosed is 0, no current is enclosed, therefore, the magnetic field in the interior of the toroid is 0. Therefore, B equal to 0 in the interior region of hollow ring or interior region of the toroid. Now, let us look at the point Q. In the same way, we will apply the Amperian circuit law. We will first construct Amperian Amperian circular loop of radius r2, and then we apply in the same manner. So, there we will get B dot dl is equal to mu naught times IE. There we will calculate what is the value of B. In the same way, it is going to be 0. How it is 0? Let us see. Now, look at it. Consider a point Q just outside the toroid, just outside the hollow ring, such that it is at a perpendicular distance, or it is at a distance r2 from the center. Distance r2 from the center, right? The same point I have drawn here. And now I want to calculate magnetic field at this point Q outside the toroid, exterior of the ring. So, what I have to do? Again, I have to draw an Amperian circular loop to include the entire current, to include the entire toroid. So, to enclose the point Q be the point at a distance r such that it is exterior of the ring, such that r2 is very much greater than r2 is very much greater than the average radius of this. R2 is very much greater than the average radius of this ring. Then construct Amperian circuit law, construct Amperian circular loop of radius r2. Then applying Ampere circuit law, B dot dl gives us mu naught times IE. So, that gives us B into 2 pi r1. So, here it is 2 pi r2. B into 2 pi r2 equal to the current enclosed. The current enclosed here also becomes 0. Why? The amount of current that is emerging out, look at it. The amount of current that is emerging out from each turn is equal to amount of current that is entering in. As I have shown you, the number of dots represent the the number of currents that are emerging out from each ring. 1, 2, 3, 4, 5, 6, 7, 8. For my reference, I have taken 8 number of the currents emerging out, and same number of currents are entering in. 1, 2, 3, 4, 5, 6, 7, 8. 8 currents are entering in. So plus 8E minus 8 plus 8I minus 8I. So total current becomes 0. Therefore, B into 2 pi R2 becomes 0, because number of currents emerging out through each turn is equal to number of currents entering into the plane of the board. Therefore, the total current enclosed IE is again becoming 0. Therefore, B into 2 pi R2 is equal to 0. This implies again magnetic field is 0 in the exterior region of the ring. So, here it is outer region of the ring, or exterior region of the ring. So, we proved that B is 0 here outside and B is 0 inside also. B is 0 inside here, B is 0 outside. Next, we have to examine what is the value of B in the inside, or in the inside region of the hollow ring, in the inside region of the hollow ring. So, now consider a point R. Look at this. Consider a point R. Consider R internal point inside the hollow space of the toroid, or hollow space of the ring. Okay. So, let us say that at distance r, so it is at average radius distance, let us say it is at distance r. Okay. Here I am considering here. So, it is at distance r. Now, again I am constructing Amperian circular loop. Construct Amperian circular loop. Amperian circular loop of radius small r. Apply Ampere circuit law. If you apply Ampere circuit law, we get B dot integral of B dot dl is equal to mu naught times the current enclosed. So, you can just see the current enclosed by this point, which is at average distance, average radius r, will be only confined to this particular Amperian loop, So, this includes the current which is entering only, the current which is entering perpendicular to the plane of the board. So, that is going to be taken as positive current. So, it does not include the current that is emerging out. So, it includes only the current entering in. Therefore, we need to calculate what is that current entering in. Therefore, B dot dl, if you calculate, it gives you B into the circumference of this Amperian circle, the circumference of this Amperian circular loop, that is 2 pi into radius, average radius r, is equal to mu naught times IE, where I need to calculate what is the value of the current enclosed. Yes, now you can see the result of Ampere circuit law is B into 2 pi r is equal to mu naught times IE, where IE is the current enclosed by this Amperian loop of radius r. Now, I need to calculate IE. How do you calculate? Here IE is equal to, look at this, through each turn, the current entering is I. Therefore, what is the current that is entering through all the number of turns? So, that is calculated as per turn it is I. per turn it is I, therefore for the entire number of turns. So per turn if you calculate it is going to be I. Therefore you can see per turn the current entering, the current that is enclosed is I, therefore for total number of turns, here total number of turns that we have assumed is n, therefore for total number of turns it is n times I, where n is the number of turns, where n is number of total number of turns of the winding, turns of the winding of the toroid. Therefore if you just substitute, we get B into 2 pi r is equal to mu naught times Ni. So this suggests that B is equal to mu naught n upon 2 pi r, n upon 2 pi r into I. So we know n is the total number of turns for the entire circumference, average circumference of the toroid. Therefore n by 2 pi r gives you number of turns per unit length, because the total length of the whole wire that is wound is 2 pi r, where r is the average radius. Therefore this can be written as mu naught times small Ni, where small n is equal to n upon 2 pi r. So this is how we get the equation for magnetic field due to a toroid. So magnetic field due to toroid is given by B is equal to mu naught Ni, where mu naught is permeability of the free space. Again we consider the space in the hollow region of the toroid as the space as free space, vacuum or air. So we consider mu naught permeability of free space, n number of turns per unit length, that is capital N by 2 pi r, where 2 pi r is the total length of the wire of average radius of the ring r. So total length of, we can say, the interior ring. So that gives us the magnetic field. Again magnetic field is directly proportional to the current, and it is directly proportional to number of turns per unit length, how closely the turns are wound, how closely the turns are wound, that depends, that's how it depends on the number of turns per unit length. So in the next session we will discuss some numerical problems on the toroid, and then we will go ahead to discuss about the force between two parallelly placed current carrying conductors. Thank you, have a nice day, bye.